So this is part 2 of section 9.5, alternating series. Just to summarize what we have so far, we have the alternating series test. The alternating series test says that if I have an alternating series, I recognize that alternating series by saying -1 to the n minus 1 power or -1 to the n power. It actually doesn't matter. That series converges if b sub n is decreasing and the limit as n approaches infinity is what that's supposed to say. And the limit as n approaches infinity of b sub n equals 0. So as long as the limit is 0 and the terms are decreasing, the series converges. All right, and just a note, if the limit as n approaches infinity of b sub n is not 0, let's say it's 4 or something, then we know that the series diverges, but it doesn't diverge by the alternating series test. It diverges by the nth term test. So if the limit of the terms is not 0, we still know the sequence, the series diverges, but the reason isn't AST, it's nth term test. We'll see, I think, an example of that soon. And then the other thing we have is the alternating series remainder theorem. So it says if I'm estimating an infinite series that is an alternating infinite series using the finite nth partial sum, S sub n, then the distance from my, say I add up 100 terms, the distance from that to the actual sum is less than the next term, the 101th term. All right, so let's see that guy in action. So let's look at the sum from n equals 0 to infinity of -1 to the n over n factorial. Okay, so then this sum, I didn't put the n minus 1 this time. That means the first term is negative. So, you can look at what this would look like. I would have -1 over 1 factorial, and then it would be plus 1 over 2 factorial, and then minus 1 over 3 factorial, and then plus 1 over 4 factorial, etc. And you can see that these terms get very small very quickly. Now that fact means that the series is going to converge very quickly. So first we're going to notice that this series converges by AST, the alternating series test, because b sub n is decreasing and limit as n approaches infinity of 1 over n factorial equals 0. Now, so notice I don't need, when I'm looking at the limit as n approaches infinity of b sub n, I don't need to include the -1 to the n, because b sub n doesn't include the -1 to the n. So if you look at the way the series test is formulated, we separate out the b sub n, that's the terms like 1 over n, we separate that out from the alternating part. And if that positive part, the limit of that is 0, then the series with its alternating term converges. All right, so we already know that the series converges. So what if I want to estimate it to 5 decimal places? So how many terms do I need to add to get 5 decimal accuracy? All right, so another way to say that is that I want r sub n, the absolute value of r sub n, to be less than or equal to 0.00001? Yeah, 1, 2, 3, 4, 5. Okay. All right. Now, what I know is that the absolute value of r sub n is less than or equal to b sub n plus 1. And b sub n plus 1 is 1 over n plus 1 factorial. So what I need is for 1 over n plus 1 factorial to be less than or equal to 0.00001, which means that I need n plus 1 factorial. So you're often going to be flipping over a fraction and inequality. Don't forget, when you do that, you reverse the inequality. Greater than or equal to 100,000. Now, you can use your calculator to determine the amazing fact that 9 factorial equals 362,880, which is and 8 factorial is less than 100,000, 9 factorial is more than 100,000. So factorials get very big very fast. Since I need n plus 1 factorial to be greater than or equal to 9, n equals 8. And so that means that 8 terms, I will need 8 terms. And it typically happens that fractions, series that have n factorial in the denominator will converge very quickly like this. And that's nice, it turns out, because a lot of the important series that we're going to be looking at have that n factorial in the denominator. All right, so with this in mind, let's look at some other examples. Let's see, maybe I'll pull this and have it be handy. Pull this page. All right, there we go. Excuse me. So I'm going to look at some examples, exercises from the Stewart-Kokoska 9.5, which is page 697 of your online text. All right, so the first one I'm going to look at is, centered, there we go. All right, the first one I'm going to look at is number 12. So number 12 just gives you this, negative 2/5 plus 4/6 minus 6/7 plus 8/8. It was nice of them to give us that instead of 1 so we could figure the pattern, minus 10/9. All right, and then plus, etc. So my job is to determine whether that converges or not. So what I need to do is find a sequence that matches this. So first of all, we need to know what b sub n is, right? So I noticed that the first term is negative. So I'm going to have negative 1 to the n. If the first term was positive, I would have negative 1 to the n minus 1. All right, then the next thing I need to do is get a handle on what the patterns are of these fractions. Well, in the numerator, I see even numbers. So the numerator of this fraction is 2n. In the denominator, I see we're going up by 1, but we started at 5. So I think if I do n plus 4, then remember when we start at n equals 1, we're going to have 5, 6, 7, 8. All right, so that's what b sub n is. So what we're really looking at here is the sum from n equals 1 to infinity of negative 1 to the n of 2n over n plus 4. All right, so now that's an alternating series, and I need to determine if it converges or diverges. So what I need to do is look at the limit as n approaches infinity of b sub n. So I actually have a little bit of conflict here because I'm normally referring to b sub n as being just the positive part, not the alternating part. So what I really should say up here is negative 1 to the n times b sub n. Really, the b sub n is equal to 2n over n plus 4. All right, so the limit as n approaches infinity of 2n over n plus 4, and even a kindergartner knows that that is 2. Everybody knows that's 2. Also, kindergartners know that 2 is not equal to 0, so the limit is not 0. So that means that the series diverges. But remember that when we say the series diverges because the limit is not equal to 0, that's really nth term test. So it diverges by nth term test. What's really happening, if you look at the full set of terms, negative 1 to the n, 2n over n plus 4, all right, you have 2 up here and negative 2 down here. And so these are sort of competing limits. And as the series, as the sequence values go to 2, right? So all the positive ones are the odd ones, so they're going to positive 2, but the even ones are going to negative 2. So what's actually happening between what's actually happening to negative 1 to the n times 2n over n plus 4 is that limit does not exist. The limit as n approaches infinity of negative 1 to the n times 2n over n plus 4 does not exist. So because the terms are not coming to a single value, you can make an epsilon argument if I put epsilon around either one of these limits and make the epsilon be less than 1. Eventually, there will always be points jumping out of my epsilon band. So that limit does not exist. The series diverges by nth term test. That's all we have to say about number 12. All right, number 18. So watch how easy this is. Number 18. We have the sum from n equals 1 to infinity of negative 1 to the n e to the negative n. So what makes the problem easy in all the problems in this section, when you spot them on the AP exam, this right here tells you you're looking at an alternating series. When we see that negative 1 to the n, we know we're in alternating series land, and all we have to show is that the sequence values decrease and that they approach 0. So all we have to do is look at the fact that e to the negative n is a decreasing function. right? So I have to know, what that looks like. E to the negative n looks like that. That's e to the negative n. I mean, it's really e to the negative x, continuous function. E to the negative n is going to be points that follow that line. E to the negative n is an even function, and limit as n approaches infinity of e to the negative n, well, that's limit as n approaches infinity of 1 over e to the n. This is a fraction whose numerator is bounded, denominator increases without bound, therefore that limit is 0. And then you get to just say the series converges by the alternating series test. And that's all there is to it. So number 32, for example. Number 32, I have sum from n equals 1 to infinity of, the way they state it is like this, negative 1/3 to the n over n. That's a sort of a pretty weird way to write that, because it's easy to rewrite this as the sum from n equals 1 to infinity of negative 1. Is it not like that? Here, wait, let me try again. It equals the sum from n equals 1 to infinity. Yeah, I guess I like that. Negative 1 to the n over, and then the denominator, just have 3n times n. That's all you have there. That's just rewriting it in a little bit more convenient form. All right, now the question asks, how many terms do I need to add up? How many terms for the absolute value of the error to be less than 0.0005? By the way, we can tell the series converges. I don't think they asked that question. We can tell the series converges by alternating series test, because if I look at just the positive part of this, so I look at it as sum from n equals 1 to infinity of negative 1 to the n times 1 over n times 3 to the n. So here's my b sub n, my b sub n. And the limit of that is 0, because the numerator is bounded and the denominator increases without bound. So limit as n approaches infinity of 1 over n times 3 to the n equals 0, therefore the series converges. But that's not the question. The question is, how many terms do I have to add up to get the remainder to be less than 0.005? So the remainder is always greater than b sub n plus 1. So b sub n plus 1, this is our remainder theorem. B sub n plus 1 is less than 0.005. So I have to solve 1 over n plus 1, 3 to the n plus 1 is less than 0.005, because that's what my b sub n is. There's b sub n here. So I just have to say b sub n plus 1. So one important thing, so b sub n plus 1 means I'm plugging in n plus 1 where the n's were here. Then I just have to solve that inequality. Now, but this inequality is by no means trivial to solve. You can't really solve it analytically by any means that I'm aware of. But let's at least do the inversion on both sides. So we'll say n plus 1 times 3 to the n plus 1 is greater than 1 over 0.0005, which is 2,000. All right, we'll solve that. So the only way we're going to be able to solve that is graphically. So if we look at the y equals, I already put that in here. So here's x plus 1, 3 to the x plus 1, and I want to know where that's greater than 2,000, so I put another function, 2,000. And then I thought about my window for this one. I thought that I probably wouldn't need a whole lot of terms to get there, since this geometric series is going to increase very rapidly. So my x's, I only went from 0 to 7. I do know that I'm looking for a number that's larger than 2,000 for the y, so I ran my y's from 0 to 2,500. Since I'm using a large number for my y max, I need to have a corresponding y scale. I y scaled by 1,000. I don't know why my x scale is 5, basically, because I didn't think about it. So now we graph it, and here's the exponential function. Here's y equals 2,500. I need to know where they meet, so I do second calc intersect, and it asks for, is this your first curve? It's not really clear which curve I'm on, so maybe I get off it a little. First curve, second curve, intersection, and my guess and we get x equals 4.38. But I can't use 4.38 because n is a natural number. So I just use the next larger natural number and say n is greater than or equal to 5. So I could say n is greater than 4, or I could say n is greater than or equal to 5. Either way, I'm saying I need to add up 5 terms. So we need to add 5 terms for an absolute value of our error to be less than 0.0005. And basically that is how you do these problems. And armed with that information in these examples, I believe you can do your homework, which I'm now assigning, which is Kokoska-Stewart, 9.5, page 697, number, here we go with my list, 11, 13, 19, 23, 33, 35, 37, 39. And that will be due by this Friday, which I think is the 20th, right? Friday, 3/20 by 8 p.m. And you have to email it to me. All right, so I look forward to getting lots of emails from people who are getting this homework done and getting also their back information done.